guys have this chart also already printed off. Okay? It was on the same sheet as the parabolas and the ellipse and the circle one, so hopefully you have it already printed off. If not, you can still print it off. The unit notes are underneath the parabolas section on infinity. So hyperbolas. This is the last of our conic sections. Okay? So this is the last new shape that we're going to learn. If you look next week, we still have another section after this, and that section after this is putting all four of the shapes together, and you have to determine which one you have. I know. No, there's not an equation for it. You use your four standard forms. We'll learn about it on Monday. It's not that difficult. Don't worry. Okay. So that's what we'll talk about next week is when you have an equation, how do you determine which one you have? And I'm end up taking a test on this next week, Thursday. So a hyperbola. The definition of a hyperbola is a set of all points in a plane such that the absolute value of the difference of their distances from two fixed points is constant. The difference between a hyperbola and an ellipse is an ellipse talked about the sum of the two distances were constant. Here at the hyperbolas, it's the difference of the distances are constant. And then if you look at their standard form, the standard form for a hyperbola is x minus h squared over a squared minus y minus k squared over b squared equals 1. Or the same idea with just the numerators flipped. So what's different about the standard form for a hyperbola versus the standard form for an ellipse? Yeah, it's a subtraction instead of an addition. That's the only thing different here. So if you take a look at this equation, the only thing different from this equation than the ellipse is the subtraction sign. Okay? So that subtraction sign is going to make the difference between whether we have a contained shape of an ellipse, which is contained within itself, or if we have the shape of a hyperbola, which is not contained, which is this shape down here on this graph, which we'll get to. But it's not a contained shape, so it extends out forever in numerous directions. The direction of the transverse axis, what you need to know is that the transverse axis is the way that the direction in which the hyperbola is opening up. So a hyperbola opens up instead of being closed into one another. So if your x value here is first, okay, that means that you are opening up horizontal. So your hyperbola will open up horizontal. So we'll be opening up both left and right. Okay.
Haven't we done ones already kind of like this?
No, we have not. Parabolas are open up, but they do not have the same shape or the same properties that a hyperbola does. Here, the other option is that if our y minus k squared comes first, then we're opening up vertical. So vertical is we are opening up and down. So whatever variable comes first, that tells us the direction in which our hyperbolas are opening. So if the x comes first, that means that our hyperbolas are going to open up in the x direction, so left and right. If the y's come first, we're going to open up or down. But then the other information is, you'll notice the same. The center is at HK, okay, which is what we would expect it to be at. That's what the center for the ellipse was. That was the center for the circle. Foci points are the same. You find it the same way by adding and subtracting some c value. So the foci points, when we have our x first, is we take our h value and we add and subtract a c. To find the foci points for when the y is first, we take our k value and add and subtract our c. This time we're going to find our c for our foci points slightly different. Instead of doing a squared minus b squared, we're going to do a squared plus b squared. Okay, so this is where the other day I said notice the sign that's in between the two fractions and how you find c. Those have opposite signs. So here for a hyperbola, you are subtracting in your standard form, and how you find c is you add your a squared and b squared together to find your foci points. Okay? For an ellipse, we were adding in standard form, and you ended up subtracting your a and b. And your two foci points are going to sit inside of each of the hyperbola. So your foci points would be the 2 points right inside of it. Just like how when we had parabolas, the focus was inside of the parabola. Same idea here for hyperbolas. The focus are going to be inside of the two different hyperbolas.
You have to add the h to the c, and you also have to subtract the h to the c?
Yeah, because we have two values. So we would add it to get this focus point on the right, and then we would subtract it to get the focus on the left. So we'd both add and subtract the c. Same thing we did for ellipses. We added and subtracted the c.
Then what's that equation?
That's how we find our c. In our standard form, there is no c here, is there? There's just a squared and b squared. So in order to find how far away each focus is from the center, we're going to have to use the formula z squared is equal to a squared plus b squared. And that is derived from the Pythagorean theorem. And here, your focus is the furthest away from the center. So that's why c is where we would expect it to be in the hypotenuse spot. So then we also have, not only do we have a center of a hyperbola, we also have vertices for hyperbolas. Okay, so down here on this diagram, here's where the center is. Okay, so that's the center. Here we have a focus point. Here we have a focus point. We have our two hyperbolas. This one is opening up and down, so this would be a y minus k squared would be coming first here. And then we have vertices. Vertices are those points of the hyperbola where it comes down to, just like the vertex of a parabola was the lowest or the highest point. Here for hyperbolas, we have two vertices. That would be one of them, and that one would be the other. So it's the low and the high point of the two different hyperbolas that we have drawn. So we have two vertices. To get to the vertices from standard, we have to take our h value or our k value, depending on which way we're opening, and we add and subtract a. So we're actually going to be able to find these pretty easily because we're going to graph them similar to how we graphed ellipses, at least the start of it similar. So you're going to be able to plot where your vertices are.
Do you have to write which way it opens?
You should know which way it opens, but that will be on your graph. You'll easily be able to see which way. So here on this diagram, from the center to the vertex, that's a distance of a away. So from the center to the vertex is a distance of a. On the diagram, from the center to the focus point is a distance of c away. Okay, and then we'll see where b comes up in a little bit. Then we have two different axes for hyperbolas. We have the transverse axis, which is the way how it opens. That has a distance of 2a. What does that look like from our ellipses? 2a for our ellipses represented what?
Your major.
The major, okay. It's called the transverse axis for hyperbolas because it doesn't necessarily have to be larger than the other one, okay. The conjugate axis is 2b, which for ellipses we called 2b the minor axis. These have slightly different names because the transverse does not have to be bigger than the conjugate. Transverse is going to be the one that has your vertices and your focus on. Conjugate is going to be going your other way. Okay. And using those two values will be how we start our graph. It's the same way how we started our graph for ellipses, by counting up and down from our center and left and right from our center. And then we have these asymptotes. And the asymptote equation, this is actually just point-slope form. Okay, point-slope form was y minus y1 equals m times x minus x1. Okay, that's your point-slope form. So this comes from point-slope form. It starts with y minus k and x minus h instead of y minus y1 and x minus x1. Because we know k and h are going to be part of your graph. It's going to be the center point. So that gives us our point. And then your slope here is dictated by, when you think about slope, you do rise over run. So your rise value would be attached to your y, and your run value would be attached to your b. So here your slope is a over b, because a is attached to our y and b is attached to our x. For the other, rise over run, our rise would be b, because that's the one attached to our y, and our run would be a. So this is just point-slope form. Okay, and it says plus or minus because we're going to have both the positive version of the slope and the negative version. The equations of asymptote are what allow us to actually graph it. So here are the two equations of asymptote on that graph. And if you notice, the hyperbolas aren't going to cross them. They're just going to keep getting closer and closer and closer to them. Same way how when we talked about asymptotes earlier in the year, our graph just gets really, really close to it and never actually touches it and it never actually crosses it. We're going to take this information and we are going to try to graph a hyperbola and then name all the information about it. Okay, I'm going to show you how to graph it first, just by looking at the equation, and then we're going to take it and write all the information from it. So here's our equation. X squared over 9 minus y squared over 4 equals 1. Okay. So some of this stuff, we'll write down some of the information along the way because we're going to have to use it to graph. But we're going to start off by doing the same stuff we did for an ellipse. So we're going to start out by thinking about where the center is. So where would the center here be? Yeah, 0, 0. So we see that the center here would be at 0, 0. So you're going to put a point at your center. Now to graph an ellipse, what did you do with the value that was attached to the x? So like here, it's x squared over 9. So what did we do with that 9 value? Yeah, we took the square root of it, so it's the square root of 9. 3, and then we went 3 each way in the x direction. We're going to do that same thing here. So since 9 is attached to the x, we're going to go 3 each way in the x direction and put a point there. What would those 2 points represent?
Like the way it's going to open?
Yep, exactly. It's going to open left and right. It's going to open up from these 2 points. So those 2 points would be called the vertices. Okay, so let's write down where those 2 points are. So what 2 points did we get there?
3 and 2. Or negative 3, 0.
Yep, negative 3, 0 and positive 3, 0. We can just write that as plus or minus 3, 0. And if you looked at your formula said you took your h and you added and subtracted a to it, which is exactly what we did. Yes?
How did you know that those were the vertices?
We know that these were the vertices because our x comes first. So since our x comes first, we are going to open up left and right. So those two would have to be our vertices. Okay, so next up, now look at the value that's attached to our y. So what's attached to our y? 4, so it's the square root of 4. 2. So from the center, we're going to go up and down 2. Now, when you had an ellipse, what did you do with those 4 points? Yeah, you connected them and drew the ellipse in. For a hyperbola, though, we go out. So what we're going to do with these 4 points is we are going to create a box out of them.
So those are vertices too?
Nope, those are not vertices. Those help us create the box. Our vertices are only the 2 points that are going to be at the ends of the hyperbola. So here the x comes first. So it's got to be the 2 on the left and right. Okay, so we drew a box out of those 2 points. And this box helps us draw in our equations of asymptotes. Instead of having to look at the equations and figure out what y equals mx plus b is, this box has 3 points that each line should be. Each asymptote should go through the opposite corners and the center. So that would be one equation of asymptote. And then your other one would go the other way. So that would be your other equation of asymptote. Okay, so let's write those equations out. You just want to think of point-slope form. So point-slope form is y minus y1 equals m times x minus x1. Or you can look at the chart of information. Y minus y1, well, we don't have a y point here because we go through 0, 0. So we would just say y equals plus or minus, because we have both a positive slope and a negative slope. And then your slope is rise over run. So here, attached to the y would be our rise. So this says 4. So what's the square root of 4? 2. And then your run would be attached to the x, which is 9. So it's the square root of 9. 3, so we'd say plus or minus 2/3. And if you look at your graph, that is the slope that we did.
The y is
Rise over run for slope. That's just what the slope is. Right. And then times x minus x1, well, we don't have a point attached here to x, so we'll just say x. So those are our 2 asymptotes.
they're the same.
Yep, they're going to be the exact. You just write one equation with a plus or minus, takes care of them both. Yes. The asymptotes are the 2 lines here that the hyperbolas would get very close to but never cross. So they are going to have slopes to them. And 2/3 in this case is the slope, up 2 over 3. If you look at the box that we drew, that's the slope that we have. Okay. So now we're actually going to graph it.
The 2 that you're talking about is the plus 3 and minus 3. Right?
Correct. Plus 3 minus 3 are, or the plus 2/3 minus 2/3 are two slopes. So now to graph it, you start at your vertex, your 2 vertices, and you draw the hyperbola out towards the asymptotes. So here I'll start at this vertex, and I'm just going to draw a line going towards that asymptote and going towards that asymptote. There's my hyperbola on the left-hand side. Now I do the same idea on the right-hand side. Start at the vertex and go towards the asymptote. And there's the graph. Okay, so let's see. So we have written down the center, the vertices. We need to find where the foci points are. And we already wrote down our asymptote equations. So for here, for the foci points, they should be inside of each hyperbola. To get them, we are going to go c squared is equal to a squared plus b squared. Okay, so what's your a squared and b squared from the standard? 9 and 4, so we'd say 9 plus 4. So 9 plus 4 is 13. So c squared is 13, so c is the square root of 13. And then our foci points would be added and subtracted to our x values because we're opening up left and right here. So if you look at your center, which is at 0, 0, we would want to add and subtract the square root of 13 onto your 0, and then 0 for the y. And you just put those 2 points on your graph. So for your graph, square root of 13, what value is that around? In between which two numbers? So it's in between 3 and 4. So go out. In between 3 and 4, put a point. That's one foci point. Do the same thing on the other side. There's the other one.
How did you get that 0?
How do we get this 0 for the foci point? We went off this center. Your center is at 0, 0. We just want to move in the x direction. Your y won't change. Then we would move in the y direction. Yep, and I think that's what our next one will do. Now, when you graph these, if you get a c value to be inside of your vertex, you know you did something wrong, either with your vertex or your focus. You'll want to take a look at it. All right, and that's graphing it. Okay. So let's do a problem where we have to put it in standard.
How did you, I don't remember how you drew the box.
From
How did you decide?
we went out A, we went out B, and then we drew the box with those 4 points.
Okay, so
Same way how you start an ellipse. Same exact way how you start an ellipse is how you start a hyperbola. The only difference is instead of connecting those 4 dots, you're going to create a box out of those 4 dots. Okay? But you start the process the same exact way. Actually, let's do this one. So this is 5y squared plus 60y minus 4x squared plus 8x equals negative 76. We'll get to that when we need to discuss that. Okay. All right, so this clearly is not standard form. So what have we been doing to get things in standard form? Yep, so getting your x's and y's together. Now, from what I saw, a lot of you are skipping the step of combining your x's and y's together, and then you are not taking the value out correctly. So I urge you not to skip that step. Okay? A lot of you going right from here, seeing that there's a 5 attached to the y squared, so you take the 5 out, but you never take it out of the 60. Okay? And it's going to be really important for the hyperbolas that we actually write that step out, because we want to make sure that we don't make mistakes with this minus sign. So 5y squared goes with the plus 60y. I'm going to put a plus in between these, and then I'm going to keep it as negative 4x squared plus 8x. The reason why I'm going to put a plus in front of there temporarily is so that we do not forget to take the negative sign out of both of those x values. Okay. So here, for the y values, what number do I have to take out to complete the square? The 5. So now I see I have to definitely take the 5 out of both. And this step helps me remember to do that. So y squared plus, if we take 5 out of 60, what do we get?
12.
Yep, 12y. And then leave your blank space to complete the square. This won't be a plus anymore because we can take out, what number can we take out of the x's now?
4.
A negative 4. Yep, you'll see that the negative sign is attached to the 4, so we want to take a minus 4 out. And then we're left with x squared. Yeah, minus 2x because we took a negative number out. Leave your blank spot is equal to negative 76. Okay, so for your y's here, what do we have to add on to complete this square? Yep, plus 36. So over on the other side, what do we have to add on?
36 times 5.
Yep, 36 times 5. For your x's, what do we have to add on? 1. So then over here, 1 times negative 4. Okay? So it would be negative 76 plus 36 times 5 plus 1 times negative 4. What value do we get over here? 100? Yep. And then what do we get when we complete the square? It's 5 times y plus 6 squared minus 4 times x minus 1 squared. And then we want this to be equal to 1. So we divide everything by 100. See, this process is the same as the ellipse process. Okay? Well, the minus sign is going to dictate that. The minus sign has to be between the two. Okay? So what would 5 over 100 reduce down to? Yep, to 20. Minus, what would be the 4 over 100? 25. 25 is equal to 1. So there's our standard.
So you decided between the x and the y to come first picking the negative?
Yeah, the minus sign is going to dictate which one comes first. The minus sign has to be between them.
If the y was negative, it'd be a fact, right?
Yeah, if this 5y was negative and the 4x was positive, the 5y would be coming second. Okay? So where would the center be for this? Think carefully because we want x, y. So it would be 1, negative 6 to be the center. Because it's x minus h and y minus k. Right there it says y plus 6, so the 6 would have to be negative. I'm going to have to move this axis up a little bit.
Hey, Ms. Burns,
Yep.
if x was before the y and it was still a negative 1, would you keep it as a negative 1 or would you?
If this said x minus 1,
Yeah.
nope, it would be a positive 1, just like it is here. So I'm going to move my axis up so that this fits a little bit better on the graph. We'll go to 1, negative 6. There's my center. Okay, so now we want to put the two vertices on there. So our vertices are dictated by this first denominator. So our denominator is 20. So what's how far, in this case, up and down, because it's attached to the y. So how far up and down would I have to go from my center? Square root of 20, what's that about? Right, it is 2 square root of 5. I agree with you there. But how are we going to graph that? Yep, in between 4 and 5. So 1, 2, 3, there's 4, there's 5. I'm going to go in between there and put one of my vertices. 1, 2, 3, 4, in between 4 and 5. I'm going to go there and put my other one. Anytime we have something that's not an exact value, we just want to approximate it. Okay, so when I write these 2 points out for my vertices then, from my center, which one is changing, my 1 or my negative 6? Which way did we go? Did we go left and right? So did we change in the x direction or did we change in the y? In the y. So that means from the negative 6 point, we want to add and subtract our square root of 20, which is the 2 square root of 5. So there are the 2 vertices. Okay, so we have the center, we have the vertices. We need to now get our box so we can do our equations of asymptotes. So what's attached to the x? Here it's 25, so the square root of 25 is 5. So we'll go left 5 and right 5. And then from those 4 points, instead of drawing the ellipson, because we're doing a hyperbola, we will create a box.
How'd you know to use the 25 just because it's bigger?
We use the 25 because it's in the denominator here. It's attached to the x.
Oh, you wanted to go over that.
Right? So in the x direction, we go over 5 each way. So then how do we get our equations of asymptotes from here? How do we draw those in? Yep, we connect the corners of the box we made with our center. And then which way should this open? Where did we say our vertices were? They were up and down, so we're going to start at our up point here and open our hyperbola up. Start at the down point and open our hyperbola down. Go towards your asymptotes, but don't cross them. Okay, so we want to write those equations out. See, I'll write them up here because we've got a little bit more space up here. So asymptotes, you want to think about point-slope form, so y minus y1. So here, we do have something attached to the y value, so we're going to start with y plus 6 equals. Plus or minus, we want the rise over the run. So the rise will be the number attached to the y value. In this case, it's 20. And the square root of 20 we already got to be 2 root 5. So 2 root 5 will be in the numerator over what will our run be in the x direction? Yep, over 5. And then times, we have a point for our x. We have a value attached to our x. And that's then x minus 1. So those are our asymptotes. Let's see, we are missing the foci points. Okay, so to get our foci points, we have to do a squared plus b squared. So what's our a squared and b squared here? Yep, 20 and 25. So we have to go 20 plus 25. Well, what's that? 45. So c squared is 45. So we have to do the square root of 45, which would be what? Yeah, 3 square root of 5. What are we going to add and subtract that to from? Our 1 or our negative 6? Yeah, the negative 6. We'll do 1. And then negative 6 plus or minus 3 root 5 for our foci points. When you do your vertices and your foci, you should always be adding and subtracting to the same value. Okay? And square root of 45, about how far away from our center is that? In between which two numbers? 6 and 7, so we'll go in between 6 and 7 away. So 1, 2, 3, 4, 5, 6, and 7. So I'll put one foci point there. 1, 2, 3, 4, 5, 6, and 7. So I'll put the other one there. So there's our graph with all the information. All right, we'll stop there so that I can have you try a couple of these for tomorrow. We'll do another one together tomorrow right at the start.